Welcome back. So, we're doing the field theory active matter part of the course. Thus far, we've talked a little bit about elasticity. Obviously, it's a huge subject that there are courses that last a year long for. We've talked a little bit about fluid mechanics there too. There are year long courses. Now, what I want to do is I want to assemble viscosity and elasticity and bring them under the same intellectual roof in the form of the theory of viscoelasticity. Let me remind you of what this subject is about. So I already used the example of silly putty as an example of viscoelastic behavior, but I think a much nicer one is these kinds of experiments that I show you here, which is that you have a cell or a cell aggregate, you apply a load to it, and if the load is applied for a short time after you release the load, as shown on the upper right hand corner, the cell or the tissue will relax back to its previous configuration. On the other hand, if you leave the load for a long time, then and you release the load, the cell or the tissue will be permanently deformed. Those are the two limits of elasticity and viscosity. And what I think I'm trying to get across here is that in thinking about real material response of living matter, it's going to be a combination of both. In other words, it's not a smooth transition where you have strictly elastic and strictly viscous. In fact, you have a combination of both, and it depends on the time scale at which things are operating. I just wanted to give you a sense. I'm not going to talk about this in any detail, and if you want to learn more about it, then I suggest you go look at the work of my friend Atef Asnasios, who's a professor in Paris and does really fun and cool experiments. And you see in the upper right an image where he's actually using the deflection of a cantilever as a way to apply loads or to measure loads and to do exactly the kind of thing that I was just talking about. And at the bottom, there is a frequency dependent response. I'm not going to touch on that, but that's the sort of thing that many people have thought about in terms of the rheology of living materials. You could look at the work, for example, of Fred McIntosh and I think maybe Alex Levine and tons of other people. Denny Wirtz has done experiments. And Atef is somebody that I really enjoy talking to. But the upshot here is that I could do this static loading where I do a slow load and then I remove the load. I do a load and then I remove it at some time scale, or I could do these things where I drive the system at different frequencies and I look at the dissipation. So that's just to give you a sense of it. We're going to be very interested in tissue mechanics, and here when you think about the mechanics of a tissue, if I solicit it with very fast periodic loading, then it will elongate by stretching. And I use the word stretching in the upper right, or I should say Thomas Lequi uses the word stretching in the upper right, because it's elastic. You release the load and it will go back to its original configuration. If you hold the load for a long time, what's going to happen is that the cells are going to rearrange and set differently. And you can tell in looking at the top and the bottom that the orientation of the contacts between the cells has reoriented. In other words, there's somehow a net trend such that the cells have a different alignment in the presence of the load, and that means that the reference configuration has changed. It's no longer the same configuration it was when you started. And so that is a viscous effect at the level of a tissue. We're also going to think about this when we talk about the work of people like Stefan Grill, where he's looking at the C. elegans embryo, and there is a cortex. So I haven't used that word, I think, before in the course, but there's this cell cortex, which is a layer of actin, and it's the motors that cross-link those filaments, and then there might also be passive cross-linkers. And this thing at the cellular scale, if you put a load on and you release it rather quickly, then it will behave in an elastic fashion. But if I hold the load, basically the motors and the crosslinkers will rearrange themselves, and furthermore, the filaments themselves are dynamic. So this system will basically adjust. In other words, it's a bit like riding across a bridge and having the structure of the bridge depend upon the wind. Something kind of crazy like that, or having the structure of the bridge change dynamically because the load on the bridge gets larger. So that's the kind of things that are in play. Now, we know about these things, at least somewhat, and I want to just remind you of the kinds of things that you would think about in your first mechanics class if you were to follow such a course. And one of the first things that we would think about is the so-called harmonic oscillator. And if we were to do the undamped oscillator, then I would have F equals MA. In this case, here's MA, and that's going to be equal to minus KX. So this is the F, and this is the MA. And so this thing has solutions x of t equals a cosine omega t plus b sine omega t with omega equals square root of k over m. And this system conserves energy. If you calculate the kinetic energy, which is 1/2 mx dot squared, and you compute the potential energy, which is 1/2 kx squared, and you add those two things together, it will be a constant. In other words, the total energy of that system is conserved. It's elastic. I pull it off and then I release it and it goes back to its original configuration. So that's elastic. On the other hand, if I have a configuration like the second one where I have a dash pot, so this object here that you see right here, this is basically, you should think of that as a piston which is in honey. And so as this thing is going back and forth, there's a drag force. And what's happening is that bleeds energy off of the center of mass motion of that mass. And so even though it starts out with some large amplitude motion, it will go away over time. And so in this case, the damped case, sorry, I can't write. So in the damped case, I will have MA, and that's going to be equal to minus KX, but then also minus gamma dx dt. So this is the spring, and this part is the damping. That's the dash pot. Notice that it's proportional to the velocity, not to the position. And it's negative in the sense that if the velocity is positive, if it's moving in the right-hand direction, the force is in the negative direction. If it's moving in the x direction, so dx by dt is negative, it'll be pushing in the plus direction. This thing, I'm not going to derive this, but the solution to this guy is a e to the minus t over tau, and then times cosine omega omega t. Maybe I'll say plus delta. So that's the solution to this guy. So notice that the amplitude decays over time. That's this fact. So this is damping of the amplitude. That's the viscous term having its effect. And so if I calculate 1/2 mx dot squared plus 1/2 kx squared for this thing, the energy is not conserved. The energy of the world's conserved just fine. But the thing is that the center of mass motion is now donated to the degrees of freedom associated with the molecules in the medium that's providing the damping, for example. So that's what we mean by viscosity. So now I'm ready to tell you about the really great paper. This is fun. It allows us to do a one-dimensional model that's relevant to tissue mechanics. I wouldn't claim that this is the last word on the subject, and so I'm not showing you this because I think it's the definitive thing that you need to know about tissue mechanics, although I think it's fantastic. I'm showing it to you because I want you to see a style. I'm going to make the point. Physics is not, this is an exaggeration, but physics is not a subject, it's a style. And so this is what it means to me to do physics to the problem of tissue mechanics and morphogenesis. So what they're interested in is how is it, for example, that a fly embryo or the fly wing undergoes the conformational changes that it does as an entire embryo, for example, gastrulation. That requires, forces. As they say here, tissue morphogenesis relies on the production of active cellular forces. Understanding how such forces are mechanically converted into cell shape changes is essential to our understanding of morphogenesis. So in this paper, I'm going to show you a video in a little bit, but let me just give you a sense of what's going on. There are pulses of myosin activity. So let's just take a look at the upper sequence. So here you have, this is a tissue. These two white cells are joined by a junction, which you see right here. And the question that they're asking is what's the length of that junction over time? Because what happens is that these myosin motors, as you can see here, they bunch up and they basically pull on that junction and shorten it. And in the second image, this one, you can see that they're elongating the junction. That's shown in these microscopy images over here on the right, and that's what I'll show you a video of. So what they were able to do is they've basically labeled the junction in the form of, maybe it was cadherin, I don't remember anymore, and then they've also labeled myosin, so they know where the myosin motors are, they know where the junctions are, the interfaces between adjacent cells, and then what they can do is by using a rudimentary image analysis, you could almost do it by hand. I'm not saying that that's the way they did it, but you could then measure the length of this junction as a function of time. And you could measure where, so that's what's shown here. This is length down in the lower left. Length is a function of time, and the blue is the amount of myosin in the vicinity of this junction as shown in this figure. So that's the kind of thing that we want to try to understand. And so what I'm going to show you is the logic, the viscoelastic logic of how they thought about it. So first of all, what they have to say is shown here, and what it's saying is that the length of the junction, if I apply a static force F, is going to be the original length, and then plus the displacement. So another way of writing this is F is equal to minus E L minus L naught. So if L is greater than L naught being the reference length, then what will happen is there will be a restoring force that tends to pull it back to its original length. And one of the things that they did that was really neat in this paper was they used optical traps to pull on these junctions and change their length, sort of synthetically. And so, at any rate, this is Hooke's law. That's what we're saying. We're saying that there is a Hooke's law, and that describes the elasticity of the junction. Then, I think this is a very clever idea. They say, well, if you pull on this thing, or you stretch it, or you squish it, what will happen is that the reference length will relax over time. Said differently, just like I showed you at the beginning, if I take a piece of silly putty and I squeeze it, if I do it fast, it'll go back to its original length. But if I squeeze it and hold it, what will happen is that the material will go to that new deformed length. And so this equation that they've written here, this equation tells us how the reference configuration length changes over time. And what I want to say is that together, okay, and I'll derive that. So I have that L is equal to L0 plus F over E. This implies that dL by dt is equal to dL0 by dt plus 1 over E dF by dt. Okay, all I did was differentiate the elastic law. Now, using the equation for dL0 by dt, I can plug that in down here, and what I will be left with is dL by dt is equal to, I have L minus L0 over tau, and then plus 1 over E dF by dt. But now I recognize that L minus L0, that's equal to minus F over E. By the way, there may be a sign issue here. So let's just stare at this equation. So if L is greater than L0, then L0 will increase. So that seems like it's the right sign, actually. L minus L0. Guess I'm curious about this minus sign up at the top. Does that make sense? If L is greater than L0, well, okay. I'm a little bit confused on this issue of the sign here, but the equation of motion that emerges from this, so I'll probably have to do some repair work. Oops. Saved by the bell. My thing pooped out. Let me see if I can get back. Okay, just 1 second. I don't know what happened here, but at any rate, what I want to say is that dl by dt is equal to um, f over e tau, and then plus 1 over e df by dt. And so the net result is that I have this equation of motion, e dl by dt is equal to f over tau, and then plus df d tau. And that's our governing equation for this problem. Yeah, so I made a there's some sort of a glitch on the sign that I'm going to need to fix, and I may well actually assign it for the students to think about in the homework. Not, I mean, I'll walk you through it, so it's not like I'm trying to punish you for my stupidity. I'm punished for that by myself, but rather to clarify the confusion that I may have caused. Okay, so what about all of this? So the thing that's really neat about what I just showed you is that there's two competing timescales. There's the timescale tau, which tells you the timescale for viscous relaxation, and then there's the timescale associated with the load. And so to be concrete, down here, this gives you an example. This is from their paper, where they basically have periodically spaced Gaussians of myosin activity. And then what you see, the three different graphs, so here this first one is where it's completely reversible. In other words, the dissipation timescale is so long compared with the loading timescale that this thing relaxes. The intermediate version, this gray one, it's going there's a net irreversible change, but it does recover some each cycle. And then this one, it's just pure irreversible. What I'm showing you here, this is what my book co-author and she and I worked out. And here, what we did is we assumed that the loading was cosine with some time scale omega, which you can actually see what the time scale of that was. And so you can see that if the viscous time scale is very long, that's the 3600 second case, then this thing just basically follows the loading. This intermediate time scale, you see that there's a net increase in the length, and then if the dissipation time scale is very fast, then this thing just elongates over time. Over on the right hand side is shown what happens if you actually use the experimental value of myosin. You can convert myosin into applied force, and then compute the theoretical elongation. In other words, this data is for myosin. You plug that into the dl by dt equation, and then you can compute the red curve, which tells you the length as a function of time. So on the left is highly idealized. That's pure theory. The myosin is periodic and perfectly periodic, and from one cycle to the next is exactly the same. And on the right-hand side, what you see is the use of the myosin density as a way to obtain the force. The one other thing I wanted to call to your attention, which I thought was fun, was that they defined an irreversibility index. What that is large delta t is the total length change during one cycle, and delta I is sort of the permanent leftover or irreversible deformation. And so what they're trying to do here is they're trying to get a measure of how irreversible things are, and that's what's shown in this right-hand graph. So pulse duration is going to, by changing pulse duration, they're changing the relative timescales of dissipation and of the loading, and that moves you from the elastic to the viscous regime. So let's see. I think that's basically what I wanted to say about this viscoelastic thing. It's a good opportunity for me to give a little bit of a problem for people to think about in the homework. But I think this is cool because it's a very low dimensional model, a one-dimensional model where we're thinking about a very important, substantive biological problem, but using what could seem like a rather sterile approach, of these sort of Maxwell Kelvin models of viscoelasticity, but in a very, very profound and interesting way. So yeah, so that's what I have on this topic for now.